Hi everybody, and welcome to the GC3 webinar series. My name is Laura Hoke. I'm a technical fellow with the Green Chemistry and Commerce Council. Today's topic is it's an innovation spotlight on greener flame retardants. And so for those of you that do not know or are not familiar with the GC3, I just wanted to give you a little bit of a background on who we are and what we do. So the GC3 is a cross-sectoral business-to-business network of over 100 companies and other organizations. We started in 2005, and our mission is to collaboratively advance green chemistry across sectors and supply chains. These are an example of some of the companies that we work with to advance our projects. And today's webinar is the first in a series of webinars that is supporting a new initiative that we started last year called the GC3 Green and Bio-Based Chemistry Startup Network. So the Startup Network is focused on supporting the growth of innovative green and bio-based startup companies. So we try to do this by providing visibility for these companies and highlighting their really great technologies. So this webinar is an example of ways that we do that. We also organize meetings. So two meeting program covers you see here on the left are two recent meetings that we've done that have sought to help connect startups with more established chemical suppliers, brands, retailers, and investors who can serve as strategic partners. And we really also seek to advance the discussion on how we best can accelerate green chemistry innovation. So we have three really great speakers today. So the first, we've invited Liz Harriman, who is the Deputy Director of the Massachusetts Toxic Use Reduction Institute, to moderate and also to give a little bit of a background on flame retardants in general and why we are seeking to find greener alternatives. She has a lot of experience in this, so we're really happy to have her here today. And then we have Amit Paul, who will be speaking after Liz, who's the Managing Director of Paxymer. And we also have Jan-Pleun, who's the VP of Research and Applications of FRX Polymers. So with that, I would like to turn it over to Liz Harriman to give the introduction.
Thank you, Laura. Can everyone hear me? Assuming okay. So I'm going to give just a brief introduction for those of you that are sort of new to this topic. The objective of flame retardants, of course, is fire safety. So why are we using the flame retardants? Because much of our built environment and consumer products are made of fuels, plastics, synthetics, fibers, and foams. And the flame retardants are an attempt to delay the ignition of those flammable materials. So we often use them because they're required, for example, by fire codes, Underwriters Laboratory, the NFPA, or perhaps to meet a test standard someone specifies, like an ASTM test standard. You all may be familiar with TB 117, which is a California flammability standard for furniture. It's been responsible for much of the added flame retardant in furniture and furnishings. That was recently updated in 2013 to change from an open flame to a smolder standard. You'll hear a little bit more about how some of those tests are done. And it is now easier to meet those test requirements without added flame retardants. So where are flame retardants used for plastics? This slide gives some of the many examples. Some are things like electrical products where there are concerns about the electricity or the heat actually starting the fire and then involving the plastic housing or wire insulation, for example. Others are products with a lot of potential to contribute to a fire if they're subjected to a flame or, for example, a smoldering cigarette. So there's been a great deal of controversy and investigation about which applications benefit from flame retardants in a significant enough way to make it worth the hazard of the flame retardants, which we're going to touch on in a minute. So we want to always evaluate that critically. We want to look at the root cause of the fire and evaluate options. And then if flame retardants are warranted, we want to use the safest solution possible. And so today you're going to hear about two of those safer solutions. So what kinds of substances are the flame retardants? Many of them are halogens, so that's bromine, chlorine, fluorine. Brominated flame retardants have been around quite a while, as have chlorinated. The newer ones for those are polymeric, meaning they're making polymer chains out of the brominated flame retardants. Phosphorus, you're going to hear some more about those today, and sometimes phosphorus plus halogens. Antimony is a metal that is used as a synergist for the halogens, so it makes the halogens more effective as a flame retardant. Additional ones are nitrogen substances, for example, melamine, which is used in intumescent flame retardants, which make a thick foamy char layer when subjected to a flame. And one of the newer ones are nanoclays, and I think you're going to hear a little bit more about those as well. So some of the concerns. So now we know generally what they are, where they're used, and why we use them. So what are the concerns? The halogenated flame retardants are a particular concern, and of course that's a webinar series all on its own, but I just want to point out a few of the more important issues. They are endocrine disruptors, developmental and reproductive toxins, and they're persistent and bioaccumulative. So that means they're widely found in the environment, in everything from bird eggs to large mammals, and including in human breast milk. There's a great quantity still in products out there, and so that's all going to go to ultimate disposal, and so that environmental load is going to continue. And as we study them more, we're increasingly concerned. There are regulatory restrictions, such as in the EU under the ROS and REACH programs, and increasingly manufacturers, brands, and retailers are restricting their use with their suppliers. So what we really want to make sure is that we don't end up with regrettable substitutions. The halogenated substances aren't the only ones that we have health and environmental concerns with. There's a lot of good work in comparing various alternatives. For example, EPA's Design for the Environment Alternatives Assessment on DECA BDE, which assesses a lot of the alternatives. But we also know that moving from something we know is bad to something we know less about is rarely a good move and often becomes a regrettable substitution. So when we discover the newer substances in the environment and in our bodies, and then we discover health and environmental and ecological concerns, that's a problem. So we always want to try to be careful to only use them when we have to, and to then move to safer substances, ones that we've tested and ones that we know are going to be an improvement. So I'm going to turn this over to Amit.
Hi everyone, so I hope that I'm online now. I'm the first out of the solutions that you will hear presented today. My name is Amit Paul. I have been the Managing Director of Paxymer since 2010. Paxymer is a family-owned company. We're based in Sweden. And we have a novel synergistic technology for achieving flame retardancy in polyolefin plastics. I will get into details about all of that in a minute. Basically, synergistic means that our technology boosts other halogen-free flame retardants and make them competitive or more competitive. And we work with functional polymers, so it's a very unique solution, one could say. We're also a member of the GC3 Startup Network, and I will tell some more about our story and how we got into this. But to start off, I wanted to give a few minutes of background about green and flame retardants in general. Where are we today? What are they? I also want to talk a little bit about flame retardancy standards and our view on that. And then I will wrap up and give some more details about our technologies. I hope that should be useful to you. If we look at where we are today, from where we're sitting, we see macro trends where cheaper materials are required and greener materials as well. There is an increased producer responsibility through legislation, and that's really something that seems to be pushing the trend towards greener and safer alternatives. There is a perception that there's a lot more regulation, and there's definitely a lot more regulation in the pipeline. However, this seems to be dragging out, so surprisingly, to some of you probably, I would say that the regulation is not really one of the key drivers at the moment. The key drivers that we see is a revision of fire standards. So there is a revision ongoing about how do you test to make sure that things are flame retardant and that they are actually safe, exactly what Liz was talking about before. Do we achieve what we're actually looking to achieve? There's also a revision on what should be flame retardant. And also this push from brand owners and OEMs to encounter this producer responsibility where you have restricted materials lists and you're really moving to look at what types of substances you're using and the issues with them. Those are main drivers. Then you have legislation or threat of legislation. I think the challenge that we're facing in a nutshell is basically a focus on the holistic, balanced product performance. So that means that you want to meet the product performance, you need to meet the fire performance and the commercial requirements as well. That's quite a challenge in a lot of cases. So talking about green flame retardants, this is kind of what Liz was already describing, but it is, I wanted to highlight these combinations of letters that are that you would probably come across when you start looking into flame retardants. So PBT is the EU nomenclature for persistent, bioaccumulating, and toxic, and that's basically what's being restricted under REACH. When you talk about POPs, it's a similar type of definition. It's similar substances, but that's the Stockholm Conventions. That's an international wider convention that uses that type of language, and it means persistent organic pollutants. Brominated flame retardants are both typically both of these classifications. Let's talk about REACH and CLP. There are, for instance, the green screen, which is quite a useful method for screening and evaluating risks, especially, and then you talk about the hazard and risk phrases connected to substances. And then the CMR, the carcinogenic, mutagenic, toxic to reproduction, and EDC, the endocrine disrupting. Those are kind of up-and-coming terms that are being very, very widely discussed, especially in Europe, and they are prone to be legislated on soon. That's definitely something that's a lively debate right now, so to say. In the industry, we talk about eco-friendly, which could then actually also entail these polymeric brominated flame retardants, but if you talk about halogen-free and non-brominated, then you're for sure in the realm that we're talking today. And then finally, the other aspect of this is the safety part of it, and that is really where we're headed, and I want to spend a few minutes on talking about standards. And when you talk about standards, there's been a big shift. But what fire marshals mean when they talk about fire safety, we're talking about reducing fire spread, so meaning lower peak heat release rate, lower fire growth rate, that's the FIGRA, and also reducing dripping, because burning drips will reignite materials and spread the fire. And then we're talking about smoke, so we're talking both smoke opacity and smoke toxicity. And you're looking for certain aspects of smoke toxicity. And then I have that little circle down there, flame retardant versus flame resistant, and I don't think people who work with other things than flame retardants think that there's a difference. But flame retardant, and that's really the realm where we are at now, when you're talking about thermoplastics especially, then you are typically talking about burning materials. And these, what we're interested in is to design how they burn. So therefore we make them flame retardant. We try to control the burning process of these materials. Fire resistant would be to make them stop burning. And of course, in some cases that would be desirable, but then typically you would have to look over which materials you look at. But flame retardant, that's sort of the realm that we're in. Let me show you why it's important to make that distinction as well. This is the, well, I would venture to say it's the oldest standard in the book. It's the UL94V0 testing. It's something that we made at our lab for reference. You have Paxymer on the left. You have a brominated solution on the right. Both of these are flame retardant V0 materials, so they both have the same fire grade. This is in polypropylene, by the way. What happens when we burn them is that I would urge you to think about which room would you rather be in if this was a fire. And the difference in a fire is that you have a much bigger flame. This is 50 watts. Fire is much, much, much more intense. And you typically don't have anybody removing the flame as the test progresses. So this is kind of where we see why it's so important to design the whole burning process and not just focus on meeting a specific standard. And apart from the safety aspect that kind of comes into the standard issue is that we are moving also, there's a progression in standards, moving away from, or sort of you're starting with a material standard, a material grade, and then you're actually testing it in the component or in the application. So in the way that it's going to be used in the end, that's typically where you end up testing the material. So standards are becoming more large scale, more complex and sophisticated, and also a bit more realistic. So you are there is a big push to redesigning standards so that they actually sort of test for what the scenario is that you think is going to be the triggering factor here. So you have different standards for different applications, and there's a whole range of them basically. But a material standard isn't necessarily going to correlate to these application standards, which makes this whole field quite complicated. This is also something that I wanted to push for, because I think that we have a lot of people in the brand owners box at the moment listening, or I hope so at least. And one of the things that's important to understand is when you look at these new technologies, because these are relatively new technologies typically, you can see that there is a big sort of incentive in the material supplier part, and there's also a big incentive in the brand owner part. Material suppliers wants to push the new innovations that they've made up, and the brand owners of course can sort of take the selling points of these and market the greenness of the materials to the end customers. It's important to realize that for the subcontractors, typically switching materials, going to new materials is a big challenge. And we've seen in some cases that we've done that really a firm sort of project managing position from the brand owners is quite important to be successful in these substitution processes. And also this contact that the GC3 sort of provides between the first and the sort of a few steps down the line of the supply chain, like that type of interaction is quite important to get to these new solutions. Anyways, summing up the background part of this presentation, I would say that green flame retardants, from where we're sitting, are really a sort of the minimal common denominator. They're defined as non-persistent, non-toxic, and non-bioaccumulating. The main drivers that we see on the market are changing fire standards, but it's also the OEMs and brand owners that are pushing for cheaper and greener materials. The challenge is really to find a competitive solution that can provide a balanced performance. So that means meeting commercial processing and performance requirements. And there are several options available in the sustainable segment, but it's very difficult to find a one-size-fits-all. So that means that it is a supply chain challenge to implement these types of new technologies, because they differ in their mode of action from the brominated ones that the plastic industry is used to dealing with. And I think that responsible procurement and product specification and sort of supply chain management is really key to successful implementation, and I will show you a case of that later that we've been involved with. So, talking a little bit about Paxymer. We are, as I mentioned, a family business. We've been working with health and environmentally conscious development of polymeric materials since 1985. We stumbled into flame retardants in the beginning of the 2000s when we were approached by the Swedish Civil Contingencies Agency, and they had just sort of concluded a major study with the US fire marshals, and they found this quite horrific statistic that you see on the screen here, that if you look at apartment fires and you look at flash overtimes, in the 1950s with the Bidling technologies and materials that you were using then, an average apartment had about 15 minutes until it was reached flashover, until it was lethal conditions. In the 90s you had approximately 2 minutes to do the same thing. And part of that is the use of all these wonderful plastics that have a lot of great, really great properties that we want to use for energy conservation and lightweighting and making things cheaper and so forth. But ironically, part of that deterioration was also the effects that halogenated flame retardants had on smoke. So smoke toxicity had risen a lot, and that was also seen in that same study where they saw that cancer is highly, highly common in firefighters. But that's beside the point for this. But that sort of quote grabbed us, and we saw that it's important to look into these things, and it's important to find greener ways to make flame retardants, and that's where we started looking at it. 2006 is when we filed our first patent. In 2010, which is when I entered, was when we, as the family, broke it out into an own limited company, and since then we've been on the wider market. So what is it that we're doing? We are working with a functional polymer that boost the performance of halogen-free flame retardants. And I start talking about the safety aspects because that's kind of where we started off, you know, both the fire safety, which is the middle part of the slide, and of course the health and an environmental part of this as well. But as far as the benefits are from the fire safety, we see that these functional polymers, they actually propagate cross-linking in the backbone of the materials that we work with. And again, those are polyolefins that's compatible with. They basically, it prevents the flame spread and controls and reduces the peak heat release rate of the materials. So that means it burns slower. You control the burning process. We also see that it starts burning a bit later. We stabilize the material to some degree, so you get an increased degradation temperature. We can also see that we eliminate burning drops, and that's a big part in this sort of reignition of materials. The most visual example that most people can relate to is a curtain that burns and drops, and then it ignites the carpet, and then it goes on from there. And finally, we're also talking about smoke and smoke toxicity. So we are completely free from corrosive gases. Carbon dioxide and carbon monoxide are things that sort of come from the burning of the plastic itself, but at least we can get rid of the other stuff, so to say. So it's a big improvement in smoke toxicity as well. And as you see, it's free from persistent and endocrine disrupting chemicals. For the industry, they think that's a nice pitch and all, but this is kind of what matters to them, and I guess to you. So this is what I meant when I started off by saying that we make green flame retardants, halogen-free flame retardants, more competitive. In the left-hand side, these are solutions that are added in the compounding or molding processes. So it's molded into the plastic. And the flame retardant is typically, and that's typically the criticism of the halogen-free systems, is that they're used at quite high dosage levels. And with the flame retardants on the left here, you use a lot of halogen-free flame retardant, a little bit of base material, and then you make your plastic. And there are consequences to that. So for instance, you're going to have a tough time meeting your mechanical specifications and perhaps even your processing specs, or you have to make compromises there. What we can do is we add a little bit of our functional polymer in, which is highly compatible with the base material, and then you can reduce the flame retardant level. That is typically cost effective because the flame retardant is expensive. It typically improves the processability and the mechanical properties, and you're using less of this hazardous additive anyways, and therefore basically you also improve your environmental footprint, and you can also move away from these brominated solutions without compromising on your product performance. So here are some cases that I wanted to talk about as well. The 3M case I'm going to get back to and look at in detail, but we are doing washing machine ventilation. It's blow molded HDPE that meets the US fire requirements. We are involved in designer furniture that meet IMO and CAL-TB fire standards. We have a lot of activity going on in conduits, electrical and also optical cable conduits, where flame retardants is a big deal. We have a lot of cables going through our buildings, and these are in conduits, and there's a lot of material basically sitting in our walls, and making those flame retardant and making those halogen-free is a big issue. But I wanted to highlight the 3M case, because it's a good example, I think, of how a big brand owner can actually work to achieve this type of substitution. And basically, it was, for one, the target for 3M was to have cost and weight savings on their solutions. And the actual end of this was that we typically they make their welding masks, which is what this was, from polyamide, and we enabled them to make it from polypropylene and still do that with a retained product performance or meet the spec that they had set up. So they were looking for a low-cost solution. So of course that sort of also reflected the spec of the product, but nonetheless it's a strict requirement, and they had very high requirements in surface and on dropping tests and shooting tests and so forth. So it's a challenge to meet these mechanical requirements. And I think the success factors, and that's kind of what I wanted to highlight here, was that for one, the project was coordinated by 3M. The focus from 3M was that they wanted to have a specific target performance. They were looking at cost, they were looking at weight savings, they were also looking at specific performance metrics that they had set up in advance. They were quite open to try new ideas. So they are used to working with polyamide, but they were open to try polypropylene, and they had been trying a lot of different things basically before we came in, but once we came in, they really sort of saw that this is something that could work, and they took stewardship. They had very few fixed variables, so whatever sort of we could come up with, they were able to implement and test, and once we had a satisfactory final product, they just said, okay, let's go, and they launched it. In the end, we also had a really close three-party collaboration between 3M and Paxymer and the injection molding subcontractor, which was quite important. And coming back to what I was saying about the supply chain motivation, is that this injection molding subcontractor, for them, I mean, they run most of their machines on polyamide, and they didn't really see the benefit of going to polypropylene. And so for them, it would have been easier to just go with a polyamide solution. And hadn't 3M been so involved, I don't know if we would have ended up where we ended up. But now this product is commercial, and it's on the global markets. So I would wanted to conclude my presentation by giving a little bit more sort of technical detail about what type of materials that we have experience with, and then I'm making a bit of an educated guess for the do-it-yourself or for the what do you say, consumer markets, I'd say, where you could find flame retardants, where you would expect to find them. So if you look at compatible materials with the Paxymer technology, it's polyolefins. I mentioned that a couple of times. What does that mean? It's polypropylene, polyethylene, thermoplastic elastomers. They need to be olefinic based, but nonetheless, a lot of those. Ethylene vinyl acetate, also things as VPC, so wood polymer composite materials. These are typically polypropylene based, and then you add wood fiber from 30 to 70% depending on what you use them for, and also for TPOs. And along the lines of what I've been talking about, I'm not saying that polyolefins have the potential to solve every material challenge, but I think that it's a dynamic group. They have a very wide range of properties. There's been a lot of development going into them, and they are, I think, underused. And if you can actually fix the flame retardancy parameters of it, I think there's a lot more potential from this material group. So I wanted to kind of, if you look at the other column here, electrical power tools, power cords, conduits, cables, lamp plugs, different electrical plugs and components in general, furniture, wall cladding, insulation for walls, insulation for pipes, and also different types of housings. I mean, a lot of these are use a lot of different materials, but I think there's definitely potential to look at polyolefins. They are green, they are lightweight, they're typically also pretty cheap at least compared to the engineering plastics. And so what I wanted to leave you with was that Paxymer is an enabling technology that helps you achieve functional halogen-free fire performance, and we are definitely open to discussing projects or applications and helping you find a solution that works for you. So I'll talk to you later in the question session, and by that, thanks a lot for listening, and I'm handing it over to JP.
Okay, thank you, Amit. I'll talk about a material that we have developed at FRX Polymers, and those are polyphosphonates. And I'll give you a slight introduction on why we came to these type of materials and what the benefits are of these materials in a lot of different applications. So we already talked about the backgrounds on flame retardants. We talked about some trends that have evolved over time in terms of flame retardants. I want to specifically highlight, I would say, the two megatrends that we have seen over the last 10 years. The one thing that that was discussed by Liz and Amit gave some good examples is on halogen-free, and that basically was started in the early 2000s because of some of the legislation that came about in Europe with the ROSE and the WEEE. But the other trend that we see actually in the last, say, 5 to 10 years is that also people start to consider polymeric flame retardant solutions as one of the most safest flame retardancy approaches. So it's not only halogen-free, but even going into polymeric solutions. And even if you think about the brominated flame retardants, there's still a lot of brominated flame retardants used today. I mean, they're very effective flame retardants, besides some of the negative aspects of them. But even on the brominated flame retardant side, currently polymeric forms of bromine are being offered as flame retardants. And because of the polymeric nature of these type of materials, it's sometimes you can actually use them much more than just an FR additive. So, of course, FR is the prime importance for using these materials, but they actually can also have some additional benefits besides flame retardancy. And if you look at the market today, the Nofia Phosphonates are the only halogen-free polymeric flame retardants that are available today. So if you think about non-halogenated flame retardants, and Liz already gave a brief overview, so I will not dwell too much on this slide, but you can group them, I would say, in three categories. And those are the phosphorus, the inorganic, and the nitrogen-containing flame retardants. And there's a lot of information available. There's a lot of different flame retardants producers that make these materials. But a very nice overview for your reference to look at maybe after the webinar is brought together by PINFA, which is the Association for Phosphorus, Inorganic, and Nitrogen-containing flame retardants in the EU and in the US. So the inorganic flame retardants, we already talked about them, ATH, MDH, and aluminum oxide hydroxide. They basically work by releasing water, so as a sort of coolant and dilutant for the flammable volatiles that come off of the flames. You have your nitrogen-based flame retardants, which can be used in certain cases by themselves, but a lot of times they are used as sort of synergies or co-flame retardant with phosphor-based flame retardants. And then the third category would be the phosphor-based flame retardants. And there's a whole range of different phosphor-based flame retardants with different oxidation states of the phosphor. You have your red phosphorus, which is the most pure phosphor-based material. Then you have your phosphates, phosphonate salts, and then the polyphosphonates that I will talk about more specifically. So if you would group all of these flame retardants in this quadrant that I put here, you can see that the trends or the market preference, if you want to call it that way, is moving to the left upper quadrant, moving away from the right bottom quadrant, where you have your halogenated flame retardants, being small molecules. We already talked about the persistency, the bioaccumulation, and the toxicity of these materials. Another aspect of brominated flame retardants is that you typically need to use antimony trioxide for a lot of applications to make them more effective. Being small molecules, they can migrate from the host plastics, and then the toxicity associated with them also when, for example, you get incomplete incineration or combustion of these materials, where you can get formation of dioxins and furans. If you now see the trends within the brominated flame retardants, that recently in the last, say, couple of years, when the industry decided to move away from some of these flame retardants, new type of flame retardants were introduced. Those are the halogenated brominated materials. So the advantage is that they will not migrate from your host plastic, so they will be contained in the plastics, but still you need to use antimonic trioxide, and the incomplete incineration is still a possibility there as well. If you move to the left side, and I specifically focused here on the phosphor-based flame retardants, so not on nitrogen and the inorganics, you have your smaller molecules. Those are the phosphate, the phosphonate salts, DOPO, for example. Of course, they're halogen-free, but in some cases they might migrate from the plastic. They can negatively affect some of the thermal and mechanical properties of the host plastic. It's very known, for example, that phosphates are typically acting as plasticizers when they're used in plastic, so they will reduce your heat properties. And then if you move away from both of these brominated flame retardants, polymeric, or from the phosphor-based materials to your polymeric phosphor-based flame retardants, then basically you have all the advantages of the different groups together. So we're halogen-free, there's no migration of the materials, a very favorable toxicity profile. I will talk a little bit about it later on. One of the very important aspects is that you can look at these materials as being polymers. So it's just like another polymer that you add to your plastic. So it's very you can still use the same process, melt processing equipment. So it's melt processable. It has the additional advantage that it's transparent, so you can deliver more properties than just FR, and that's where we focus on mostly. So our material, the Nofia Phosphonates, they have a very favorable health profile and obtained a benchmark score of 3 in the green screen assessment, which is a assessment that looks at has a profile of materials. So there have been a lot of assessment done for different type of flame retardants, and a benchmark score of 3 is one of the highest that you can get. It's a score from 1 to 4, 4 being the highest. As Liz also mentioned, EPA has done alternative assessments for flame retardants like HVCD and DECA-BDE, and the Nofia Phosphonates were also recognized as one of the flame retardant alternatives for DECA-BDE. We have done a lot of work on registering our materials because we're polymers. We fall under the polymer exemption process for a lot of different countries. There's about 9 countries in the world that have this polymer exemption process, so we registered all under those materials. And in monomer, where we have our in Europe, where we have our production facility, we actually comply with all of the REACH regulations as well. So think about polyphosphonates. So the scheme that you see here is a plastic with traditional flame retardants. So typically you can see it's a small molecule. So because of the thermodynamics, these type of materials ultimately can migrate out of plastic material, and you might actually experience a similar process, not per se with flame retardants, in some daily life experiences. For example, if you buy a new car and you smell the new car smell, a lot of times it's a lot of the small molecules that still migrate out of the plastic dashboard and what have you. So if you take a polymer, you can look at it on the right side. That's more like you have a long chain which is just embedded in the polymer matrix, and it's therefore trapped into the plastic, so it will not migrate out of your material. So that has a lot of different advantages. Like I said, it will not migrate out. The impact on the host plastic properties are minimal, but one of the bigger advantages is also that you can use all kind of plastic processing methods that not per se can be used when you use low molecular weight flame retardants, or for example flame retardants that are non-meltable flame retardants and that are more present as inorganic particles in your plastic material. The other benefit that with our material, which is especially important for a number of applications, is that the material that we make, it's a plastic by itself, and it's actually a transparent material. So if we mix our materials with certain plastics, we can maintain the transparency, which is a big plus for some applications that I will highlight later on. So the product offerings that we have our homopolymer. It's again, it's a polyphosphonate. It's about 11 weight% of phosphorus. We can make a range of different molecular weights. Just depends on how far we will carry on our polymerization. It's amorphous polymer, so it doesn't have a melting point, but it has a glass transition point between 100 and 105 degrees, and we actually sell it as a plastic pellet, which is also very beneficial in terms of handling. So a lot of times when we introduce our material to customers, initially they might think it's a master batch because they see the material, it's a flame retardant and comes into a pellet, but actually it's the flame retardant by itself that we actually make as a polymer. Because of the chemistry that we use, we have a lot of flexibility to make different type of materials. So we have one group of materials which are a polyphosphonate coke carbonate material, where we have different levels of phosphor, and we can again make different types of molecular weights. And these are specifically designed to be used in polycarbonate applications, and they can actually be used by themselves. So you can actually extrude sheets out of them, you can injection mold parts out of them, and you basically have an inherent flame retardant polycarbonate. And finally, we have the oligomers, which are small molecular weight versions of the first two materials. And because of the chemistry that we use, we can actually modify the end groups of these oligomers and make them suitable for as reactive materials with other monomers. So these actually can be built into especially thermoset applications. So you can think of epoxy materials where they react with the epichlorohydrins. You can react them with isocyanides and therefore build it into polyurethane foams. So there's a lot of different possibilities that you can have with these reactive oligomers. So where we are being used, so unless where Paxymer and Amit talked about in the polyolefins, we are focused mainly on the engineering resins. So you can see specifically polycarbonates, polyesters, polyurethanes, and then on the thermoset side we have a fairly broad applicability ranging from epoxy materials, unsaturated polyesters, and phenolics. So if you look at a range of different applications, I just put here a number of examples where we are being used today. A lot of the applications that we are being used in today are in the polyesters, because we have such a good compatibility with polyesters. And you can think about fibers, monofilament fibers for industrial applications, or for synthetic hair applications that are made out of polyester fibers. Multifilament fibers for flame retardant textiles, for upholsteries, for curtains and those type of applications. Staple fibers also for the same type of applications, but also for non-wovens, for example, and then bulk continuous fibers for carpets. Because we are, as I mentioned, we can make transparent blends with polyesters. We can also be used in biaxial oriented PET films, where we can maintain transparency. So by using our material, you not only can maintain the transparency, but because we are polymeric and we are just part of the polymer phase, you can actually make films that are very thin and still maintain your transparency, but also have your flame retardancy. So this goes down to below 50 micrometers. You can make transparent films out of polyesters that are flame retardant, or for example shrink tubes for batteries. And another application area in polyesters is in polyester foam for structural applications, in addition to, for example, polyurethane foam, where we can be used with our reactive oligomers, where they react with the isocyanates and can be part of the polyols in these type of applications. Another large application area, and basically I would say one of the biggest areas for flame retardants, is in the epoxies for copper clad laminates for rigid and flexible printed circuit boards, where we not only are being used as a hardener in these systems, but also as a flame retardant. So we have both the hardener and the flame retardant at the same time. But on top of that, we offer a lot of additional benefits in terms of electrical properties. So we offer very low decay and DF in these type of applications. And again, in the polycarbonate type of applications, we can be used in structural panels for transportation, in aviation, railway, and finally in TPUs for floor coatings in aviation or wire and cable applications. So one of the bigger examples where we are being used, like I mentioned, is in fibers. That's going to be carpets, textiles, and synthetic hair. And one of the big advantages is that you can use our material and dry blend it with the base fiber polymer at the hopper. So you have a lot of flexibility on which type of polymer you want to use. You can have a lot of flexibility in the amount of phosphor that you want to add to your fiber applications. And because we are polymeric, you have no limitation in your fiber diameter. So you can spin very thin fibers, which is typically not possible if you have, for example, a non-meltable flame retardant, which will bring rise to a lot of fiber break when you apply those type of materials. And some of the tests that we have been passed is in the radiant panel test for carpets. We get a class A, and the NFP 92507 test, the typical French M1 test. And I will tell a little bit more about those tests later on. Inherent flame retardants, polyester options are available on the market. Trevira CS is very well known, but also some other companies offer flame retardant materials. But on overall, you can look from two directions. There are some disadvantages to these materials. For the producers of these type of materials, they typically make them in campaigns. So they typically make polyesters and then they switch over to build in these monomers into the polyester. But there is a limitation to the amount of phosphor that can be built in. Typically it's about 6,000 ppm. So you also have limitations to the stringency of the flame retardance test that you need to meet. And you're only restricted to the 6,000 ppm. With our material, except from that we typically give an improvement in terms of color. So when our material is being used, you can make a wider fiber. You also have better mechanicals, so a higher tenacity, but you don't need the special flame retardant polyester. So the downstream users have a big advantage that they don't need to use a specific flame retardant PET, but they can use their own PET that they use for their regular spinning of their fibers. And they can just switch their downstream equipment and add a small stream of our material into the PET. So you can do that with regular PET, of course. But the benefit now is that you could even use recycled PET. So you can buy recycled PET in the market and you can our material and thereby upgrade your recycled PET to a flame retardant PET fabric material. And then finally, of course, you can think about bio-based polyesters. You have PLA containing polyesters, PTT. You have a new material on the market, polyethylene furanoate. These materials are not flame retardant by itself, and it would be too much to build in a flame retardant monomer into the chain. But for these type of materials, you can actually add our material downstream, and that's a big advantage. So to end off this presentation, just some example of how we have been performing in this NFP 92507 test, which is the French test in Europe. It's one of the most stringent flame retardancy tests. And it actually consists of three types of tests: one electric burner test, one flame persistence test, and a dripping test. So if you look at all of the different classifications that you can get, it ranges from M1 to M4. But M1 is the most important classification that you want to get. And with the 503 test, you want to have an ignition time of less than 5 seconds. With the 504 test, you need to be less than 2 seconds. And in the 505, you should not have any droplets. So if we test materials with our material, so in the 503 test, where we test our materials, we found that we had no after flame time, so it should be lower than 5 seconds. There were no damage in the width area, very small in the length, and there was no flaming debris. So from this perspective, we classified the M1 criteria. If you have a meltable material, and polyesters are, then you need to continue with the 504 test, which is the flame spread test. Here you make holes you burn holes in the fabric, and you look how quickly the flame extinguishes, and should be smaller than 2 seconds. And in our case, there was no after flame time at all. There was no burning debris from the fabric as well. So next test that was passed, and then finally you have the what I call the dripping test, and here you look if there is ignition, whether you have flaming debris or ignition of the wool that is underneath the sample, and there was none. So when you fulfill all of these tests, you actually have an M1 rating. Then we did some additional screenings in different FR tests. We did that together with a lab in Belgium, Syntax Bell, who performed a lot of these testing, who are a known testing lab for flame retardancy for fabrics. And in the ISO 150-25, there was no after flame glow time. The EN 597, which is used for mattresses and upholstery bed bases, there was no ignition. And then finally in the 13773, which is the European test for curtains and drapes, there was no ignition, and the first mark was not reached. So again, showing a very robust flame performance of our material used in polyester. So we started this development back in 2003, and in 2007 our company was founded. We all came a long way since then. So in 2012 we did a groundbreaking in Belgium for our first commercial plant of this material. This is the first time that this material is being made commercially globally. And in 2013, 1 year after the groundbreaking, we were able to commission our plant already. And in 2015, about 1.5 years ago, we did the inauguration again with together with the Flemish government. And that's where we have evolved since the concept and the idea from this material in 2003, where we are now selling our material globally, and it's available for everybody to use. So thanks a lot for your attention. Any questions, I'll hand it over back to Laura and Liz.
Great. This is Liz. Can you all hear me? So we have some questions, and I know we don't have too much time before the hour, but and I apologize, that's our phone time out here. Amit, there are a number of questions around the hazard and for example, green screen benchmark scores for your materials. So I think if you could say a little bit about what you've done to evaluate the hazard and maintain that data, whether it's available to customers, et cetera, that would be helpful.
Thanks, Liz. Yeah, like as I mentioned, I mean the approach that we have taken is a multi-mechanistic approach. So that means that our functional polymers on their own do not necessarily meet the entire flame retardancy performance. It's an addition. So that means that depending on how you formulate in the end, that's going to affect your final flame retardancy your final green screen or evaluations or performance of that. I'm happy to talk about it. So therefore, it's a bit complicated to answer it as a blanket. The functional polymers that we are using have no risk traces connected to them, and they are both sort of commercially available at large scales, and they are also fully green, so to say. And I would be happy to provide more information. Just shoot me an email and feel free to get in touch, and I'll provide you with more information about that.
Okay. Do you have green screen benchmarks for the ingredients that you're using?
We do not. We have for some of them, yes, but we do not for all of them, no.
Okay. So JP, a question about migration data. If you have that, you mentioned that the substances don't migrate out of the polymers and resins. And if you have that, could you share it with customers?
Yeah, we could. I mean, one of the main application areas, like I mentioned, is in fabrics. So one of the things that what we have been doing is typically when you have your fabric process, there's a lot of washing steps involved as well. We, for example, have washed fabrics many times, sometimes over 100 cycles, and there is no change whatsoever in our in the phosphor content that you measure in the fabric. So none of the material leaches out. So we have some of those data that we can share with customers.
Okay. One more quick question about the thermal stability of the resins using the phosphor compounds.
Yeah, so our materials by themselves are stable as measured with TGA in air and in nitrogen up to 400 to 450 degrees. So we typically process them at temperatures up to 300, 320 degrees without any issues.
Okay. Amit, another quick question. Have you used your substances in polyurethanes, particularly in clothing items? Or
it is unfortunately not compatible with polyurethanes. We need the polyolefin base to have all the commercial alternatives that we have out there are for polyolefins, so not for polyurethanes.
Okay. And a question for both of you. doing standard hazard testing is one thing. Have you tested the ingredients or had them tested for endocrine disruption? That's for either of you.
We haven't done a specific test on endocrine disruption, no.
We haven't done a specific test for that either. What we tend to do is the risk evaluation and just basically try to look at the hazard level of the chemicals that we use.
Okay, so we are at the hour. We do have a few more questions, so Laura, I assume that we can ask our presenters to answer those afterwards.
Yes, for the if JP, if you're okay, just staying a minute or two later to answer a few extra questions, we're happy to stay on the line. But I do understand if people do have to drop off, so it's up to you.
Okay, so Amit and JP, are you available to stay a few minutes?
Sure, I'm okay.
Okay, so there was a question about nanoparticles and whether those are included in your flame retardant materials. So start with Amit.
Yeah, no, they're not. I mean, we typically don't like nanoparticles that much because of the, firstly, the processing challenges that they present. It's really challenging to get them incorporated, also to verify that they remain at the nano level and not agglomerate and so forth. But then also the health and environmental aspects are tricky, and that's why we like the functional polymers and combining it with the most benign of the nitrogen phosphorus or the mineral-based flame retardants.
Okay, and I think this is for JP. Will your product work with aramid fibers?
We haven't really experienced with aramid fibers yet. I mean, we have done some work in nylons, and there is that's just in the starting phase, in the early phase. We have mostly focused on polyesters, but we do see some good effects in nylon 6, but we don't have experience with the aramid fibers yet.
Okay, and question for Amit, the polyphosphonates you said were a benchmark 3 under a green screen evaluation. Is that true for the oligomers as well?
So that's for me, I guess, right? Yeah. It's,
sorry.
Yeah. No, we don't have the class 3 because of the low molecular weight version of the oligomers. But I mean, for us, the oligomers are being used mostly as their reactive phase, so they actually react in with the polymer. So best would be to assess their green screen performance on the final stage.
Okay. Amit, this one's for you. Question about the metabolites. So in your evaluation of the hazard for the materials that you are using, have you looked at the metabolites, or the people that have been looking at them for you, have they evaluated the metabolites?
I need to check back on that. Actually, I'm not aware. I'm not. I haven't been that involved in those in the details of the evaluation. So I could check back.
Okay.
And again, shoot me an email.
So I think there's a lot of interest in the technical performance of these, but there's obviously also a lot of interest from customers and throughout the supply chain about the environmental and health profile. So I guess as transparent as we can be is helpful to all of those people. There's one more question about whether there's titanium dioxide in the solid white oligomer product. Question for the Nofia product.
Oh, sorry. No, we don't have any. We don't have any titanium dioxide in our materials. Our materials are just the polymeric materials by itself. No other additives.
Okay. I think they were wondering because it was a solid white. So I think that probably gets to most of the questions. And again, we can look through and if there are others, we can follow up with you individually. Does that sound reasonable, Laura?
Yeah, that sounds good. So I just wanted to thank our speakers again. Thank you, Liz, JP, and Amit. We really appreciate the time that you took today to share your work with us. So I just wanted to let everybody who is still on the line know that the GC3 has two really exciting events coming up. So our 12th annual Innovators Roundtable, which is our annual conference, will be this year hosted at Steelcase in Grand Rapids. It's a really great conference, brings together people from all different sectors throughout the industry to discuss how we can best accelerate green chemistry innovation throughout the supply chain. And then something that I've been helping to organize for the Startup Network, so the day before the roundtable, so on April 24th in Grand Rapids, we will be having a green and bio-based chemistry technology showcase and networking event. So we'll be having a bunch of invited startups and small companies come and present their technologies and a chance to interact and engage with these startup companies. So again, thank you very much for joining us, and we look forward to hopefully seeing you at some of our events. So thank you again, presenters, and have an excellent day.